This is HRW98P067. We have a spring we have a spring constant is fixed at the top of a frictionless plane, inclined at an angle of 40 degrees. A 1 kilogram block, is projected up the plane from an initial position that is a distance 0.6 meters from the end of the relaxed spring, with an initial kinetic energy of 16 joules. Okay, we want to know the kinetic energy of the block at the instant it has compressed the spring 0.2 meters. Alright, this is a conservation of energy problem. I know that whatever total energy I have, I got to keep that same number. So let's figure out when the block starts what its initial total energy was. Okay, now I have 3 kinds of energy that could exist. So my total energy is going to be adding up all 3 of them. Well, I've got the kinetic energy. I'm going to put a little initial on it. So initial kinetic energy plus the potential energy of the spring. Initial. There we go. And I also have gravitational potential energy. Could also exist. Now, down at the bottom, let's just call where the block starts, let's just call that height is 0. Okay? If the height there is 0, and that's what I'm establishing, then the gravitational potential energy I start with is also 0. So that's gone. The spring is relaxed, so it is not storing any energy, so this is gone. So basically, the energy that I'm starting off with, the energy it's going to have the whole time, is the initial kinetic energy which they give me. In this case, 16 joules. Okay. I need that to stay the same when the kinetic energy, when the block has been compressed 0.2 meters as well. So we do the same thing again. All right, the total energy has to equal the kinetic plus the potential energy in the spring plus the potential energy gravitational. Okay, but this time the spring is compressed, so there's going to be something here, and the block has gained height. It has gone up. I have to figure out how much, but it has happened. So I'm going to get a number for that as well. I know E already. I know it's 16. But let's go and get the other ones. So, plus, well, kinetic energy of a spring stored in a spring is 1/2 K, or K over 2, times the distance it's been compressed squared. Okay? Its potential energy is going to be mgh, where h is the height it has gained since it started. Alright, we're going to start filling some stuff in. Okay, oh, now this is going to be a little weird. Notice I've got a K and a K. Ugh. This is supposed to be a capital K, and this is supposed to be a lowercase k. Unfortunately, my K's look the same. Let's see, how am I going to tweak this? Ooh. Alright, hang on. I'm going to do a little trick here. Lowercase k has, nope, that looks stupid. Never mind. That just looks stupid. Let me try that again. Okay. Alright, this is a lowercase k. I'm going to do like in grade school, like that. Do you remember that? Do you remember doing that with a little loop in the k? Never mind. Okay. Anyway, that's what I'm going to do. Ah! Alright, anyway. Okay, back to it. Alright. So, I have a spring constant. What is that? 205. Oops. That's plus. 205 over 2. I have how far it's compressed. It's compressed 2 meters. So I've got 0.2 squared. They did give it to me in meters. That's good. I have mass. Mass was 1, I think. Yep, 1. Mass is 1. G is 9.8, like always. E is 16. I'm going to go ahead and replace that. I forgot when I started. Sorry. Okay. All I need is the height. Okay, well, I'm going to do the height over here. Need more. I've got this triangle. Basically, if the block started down here, this is 40 degrees. Okay. And I know the block moved 0.6 meters to get to the spring, and then it also compressed the spring 0.2 meters. So basically, I'm looking at 0.8 meters on the hypotenuse. I need to know the height, which is over here. So that is across the triangle, the opposite side of the triangle from the angle. So h should be the hypotenuse times the sine of 40 degrees. Okay, so h is, put that in a calculator, 0.5, let's see, 0.514, and now remember that this is not a final answer, so I'm not going to round it. I need to get as many digits as I can so I don't have rounding errors later. 0.51423, and then there's 2 zeros and some 8s, so I'm gonna stop there. That's probably pretty good. That's probably good enough. Let's see, meters. Okay, so going back to over here, I put that for h. 0.51423, that's a 4 meters. Okay, and solve for k. Basically, it's 16 minus all this stuff. So if I put all that in the calculator, I am going to get an answer. Well, okay, I'll do this. I want to leave k alone, so I'm going to subtract. This. I'm going to subtract all of this. So I get 16 minus like all of this. Okay, and so I get an answer of. Let's see, I get 6. I did this all in my calculator. I'm actually not sure if I did it right, so we're going to check. I get 6.86 joules. Let's go check that. Yep, 6.86 joules, so that worked. Let's look at part B. With what kinetic energy must the block be projected up the plane from its initial position if it is to stop momentarily when it has compressed the spring by 0.4 meters? Okay, so in this case, we're saying that when it has compressed the spring, all of its energy is stored in the spring or as gravitational potential energy because it's stopped. So if it stops, that means the kinetic energy is 0. Now, I don't know. I want to know what kinetic energy it must have started with. So basically, I'm asking, how much energy did the block have to start with in order to get up here, compress the spring for 0.4 meters, and stop? Okay. So I'm basically asking for what is the total energy, because the total energy is the kinetic energy at the beginning. So let's go find out how much total energy it has when it is compressing the spring by 0.4 meters. So, I know I'm going to need to know the height, so I'm going to go ahead and find that first, just because. Okay, so I got 40 degrees again. This time, it's got to get up the plane, 0.6, and then it has to compress it by 0.4. So basically, my hypotenuse is 1 meter. That means my height is going to be 1 times the sine of 40. Basically, I'm looking for the sine of 40 here. So the sine of 40 is 0.643, 0.64. Actually, I'm going to go further, 279. That's how far I'm going to go. And you know what? This is actually pretty easy. I probably am just going to put this in my equation, and then when I type it in my calculator, get my final answer, the calculator, won't have rounding errors. Okay, so let's find the total energy when the spring is compressed, because that's going to be, the total energy will be the kinetic energy that it started with. So when it's compressed, I've got, I've got no kinetic energy because it's at rest. So all I've got are the energy stored in the spring and the gravitational potential energy of the block. Okie dokie. So stored in the spring, I've got K over 2 times how far it's compressed squared plus mgh. Okay, so that's same K, so 205 divided by 2. It's compressed 0.4 meters, 0.4 squared plus, mass is still 1 kilogram, gravity is always 9.8 meters per second squared, and now I know my h is the sine of 40
put all that in my calculator, and I should get 22.7. Let's see if I do. Yes, I do. I get 22.69931.857. So that rounds to 22.7 joules. All right.